What do wine and synthetic chemistry have in common? More than you might think. Hi, my name is Kayla Youngblood. I'm a junior chemistry major working with Dr. Kimberly Peteren. Thank you for taking the time to look at my poster. Wine's complex flavor profile comes from several organic molecules. When wine and other alcohol are aged in oak barrels, they become infused with the oak lactone, giving it a woody flavor. The lactone structure is highlighted in red. Lactones are responsible for numerous flavors and aromas. They are also of great biological interest. Pictured on the bottom left is Peteren D, a drug being used to treat cancer. Lactone structures are also common in antibiotics. Medicines like Peteren D can have large, complex structures, making them difficult to synthesize. Chemists often adopt a building block approach. They build smaller molecules and then piece them together. One struggle is the asymmetric nature of these structures. Asymmetric molecules are similar to our hands. They have a mirror image version that is non-superimposable. Both of our hands are arranged in the same way, but a right hand cannot fit into a left-handed glove. In the same way, one version of an asymmetric compound can fit into a biological receptor and one can't. Because of this, it's vital that researchers create the correct version of a compound. The asymmetric centers in Peteren D and oak lactone are highlighted in blue. The incorrect asymmetric center can be less effective or cause dangerous side effects. However, developing new methods of synthesis is costly and time-consuming. I work on developing these new methods of synthesizing asymmetric lactones. Scheme A shows the background for this research. Previously, the Peteren group has synthesized lactones from diester structures with high yields and high selectivity for one asymmetric version over the other. We wanted to expand on this work by using a nitrile, a carbon-nitrogen triple bond, as the starting material. The Peteren reaction in Scheme A is a well-known method of making esters from nitriles. Lactones can be thought of as cyclical esters. However, the Peteren reaction requires harsh and dangerous conditions. This limits the scale of the reaction and the complexity of the synthesized molecule. Additionally, it doesn't produce the necessary cyclized product. The work by Aplander et al. Demonstrates the possibility of an intramolecular Peteren reaction, meaning the molecule reacts with itself to form a lactone. My work aims to create a lactone from dinitriles using mild reaction conditions and to examine the selectivity for one asymmetric version over another. To our knowledge, this is the first stereoselective Peteren cyclization. Scheme B shows the general synthesis of the lactone. There are 4 steps. First, reduction of the double bond, then alkylation to add extra carbons and the oxygen, then removal of the protecting group on the oxygen, and finally, the cyclization step. The alkylation step proved more difficult than initially expected. Scheme C shows several attempts with no desired reaction occurring. We tested different solvents, equivalencies of sodium hydride, limiting reagents, and finally temperature. Heating the reaction overnight was key to successful synthesis. Through several iterations with the benzyl R group and improving the purification process, our lab brought the yield up to 92%. The isopropyl R group has been more difficult to react, with the highest yield being 21%. I hypothesized that the restricted sterics of the benzyl group is actually beneficial for the desired reaction. The final steps in the reaction are removal of the protecting group and then cyclization. Currently, these steps are happening simultaneously. It means we cannot control which asymmetric molecule is formed. We get a 50-50 mixture of both. Ultimately, though, this work demonstrates that there are mild reaction conditions for the Peteren reaction. Further work must be done to improve the selectivity, though. My future work will focus on controlling the cyclization step. Initially, I considered trying to slow the reaction down enough to separate into a deprotection and subsequent cyclization step. But having less steps is beneficial because it increases the overall yield. So why not take advantage of it? Instead, I want to find a way to use our asymmetric catalyst, TRIP, pictured on the left, to deprotect and then cyclize the molecule in one step. Scheme E shows the current reaction. The purple protecting group cannot be removed with TRIP. I will examine other protecting groups in the hope of finding one that will stay on during previous steps that can be easily removed when I want to using TRIP. In this proposed reaction, depending on what catalyst we use, we could selectively synthesize one asymmetric version over another. Finally, I just want to say thank you to the NIH and UNCG MarkUStar for their support in funding this research. Many thank yous to Dr. Peterson and Josh Frost for their mentorship and encouragement. May glory be to God.